Hello and welcome to Unit 3. Unit 3 is gravitational, electric, and magnetic fields. So we're looking at three different types of fields, and we're going to talk about, first of all, what is a field. And we're starting with something that you should be a little bit more comfortable with, gravitational fields, because it's something you can better chance of visualizing. So today's goal, I can explain how gravitational fields influence objects within them and make the correct calculations to determine their the quantitative influence. What we're going to do, it's going to take a little bit, this is going to be a longer video because technically, if I taught this in the traditional style, this would probably go on for a good day to 2 days of lessons, and then you'd have 2 to 3 days of work period. So it might be a little bit more video, but keep in mind that if you get most of the video done or part of the videos done, you can still do some of the homework the next day. It's not like you're stuck. So keep that in mind as we go through. So what are we talking about today? Well, let's talk about something you already know. Recall. Force. Force is defined as a push or a pull. That's what I used in the grade 11 for a definition. So gravitational, electric, and magnetic fields are all examples of action at a distance forces. Remember that action at a distance force means that no contact is required. If you're on Earth and you jump off the top of a building, you don't have to be in contact with the ground to experience gravity. You will still fall to the ground. So you don't have to be in contact. And that's what these action at a distance forces really mean. So no direct contact is required. So action at a distance describes the characteristics of these forces, but does not explain how the results are achieved. So let's talk about the concept of fields. So fields, the terminology, and this is one of the first terms that you're going to need to understand and be able to use. It goes into that communication, being able to use proper terminology. A field is a property of space. So there's your first new definition. A field is a property of space. So this was first introduced by Michael Faraday, a famous physicist in the early 1800s. And what we're talking about, an object that in that space, we call it the source. Okay, it's called the source. It influences the behavior of what's in the surrounding space. So for example, Earth is a large mass. It's a planet. So it is what we would call the source, and the gravitational field around it is what is being influenced. So it is influencing the space around it by its mass, and that behavior we refer to as gravity in that case. So the field then in turn exerts force on the other objects that exist within the space. So we are looking at how do objects, first of all, what forces are involved, or what influence do sources have, and then objects that come in that region, how do they behave? So this example again is the presence of the Earth. So keep in mind, let's make a bit of space here. If we have the Earth, it is considered our source. Well, anyone that comes within that region is going to be influenced by gravity. All right. Similarly, we have the moon orbiting the Earth. Well, it also has a sphere of influence too. And just to make your drawing a little bit more messy, let's introduce the sun. So let's say the sun's way over here. Well, the sun has a huge sphere of influence. You probably don't want to do this on yours, but I'll do it on mine. So you'll see that there are fields that overlap. So we have the field due to the Earth. So it influences, significantly influences, all right? It doesn't actually have a boundary like that. I'm just, for people who are watching this, I'm just saying that that's sort of the significant region. The moon significantly influences that, and then the sun influences the remaining region. So you can see wherever the colors overlap, then we have an overlap in fields. And that's where our vectors are going to come into play. All right, so and clear that off here. So what we're going to start looking at today is gravitational fields. So gravitational fields, it's the first concept we're going to look at in these three areas. So we're going to look at gravitational fields, magnetic fields, and electrical fields. So gravitational fields are created by objects that have mass. And we talked about this equation. Um, in the grade 9 course, or grade 11 course. And that was the equation, force due to gravity is G m1 m2 over r squared, where G is a constant. It's equal to the 6.67 times 10 to the negative 11. And the units are Newton meters squared per kilogram squared. So that's the units. M1 is mass of source. M2, we'll say mass of object. And R is distance between M1 and M2. Okay, so the same as it was in the grade 11, so that hasn't changed. So let's take, I have two objects, 200 kilograms and let's say something mass of 10 times 10 to the 9th kilograms. I'm not actually going to do the calculations here, but what I want to point out, this is where the grade 11, if you're taking grade 11, taking this grade 12 course, you just need to breathe, don't get too panicky here. But this equation here, our force due to gravity equation, is what we call an inverse, or sorry, a reciprocal equation. It's a reciprocal function. So what does that graph look like? So I'm going to show you. Grade 12s who took advanced functions will know this already. So this is for grade 11 purposes, right? I know I've got a couple grade 12s that are squirming in their seats right now saying, sure, yeah, that's right. Okay, so if I was to graph the force due to gravity function or equation, and I'm going to keep M1 and M2 constant, and the R is what's going to vary, what we would find is that we'd have a curve that looks like this. All right, so there's what the curve would look like. So this is, for example, let's say this is the radius of the Earth right here. So what is that corresponding value? Well, if we went across, force due to gravity would be, depending on your mass, so let's say a 100 kilogram person times gravity, say 10. So that would be 100, so it'd be 1,000 newtons, for example. All right, so that's just, I'm just throwing it out there. All right, what I want to do is I want to talk about what properties stem from this relationship or this graph that I just sketched. Let's talk about that. Because it's that reciprocal function, hey, there's a couple of properties that are kind of important here. So, a couple of things I want you to take away from that. As we reduce the distance between the objects, so right here, as this goes to 0, all right, oops, I didn't really want to do that. Okay, as we reduce that, as we move that dotted line closer to the y-axis, the radius is decreasing. So as radius decreases, the resulting force due to gravity increases. And it increases significantly. So as you move toward it, if I moved the radius and did an analysis right there, you can see this is now your force due to gravity or attraction. So I'm just going to call this, say, R2. So you can see there's a significant increase between the two. So Fg increases, so that force of attraction is much, much greater. All right, so just down here, force of attraction is much greater. So the closer two objects are, and that graphically shows why that is. The second point, the farther objects get apart, so let's move the other direction now. So as we move the other direction, now I'm going to have this as R3, well, now you see the point, the force due to gravity is much, much less. So it's kind of the flip or the contra argument to number one. So as radius increases, the resulting FG decreases. So as you get farther and farther apart, force due to attraction decreases. So force of attraction is much less. All right. And the third and final point that I want to point out here with this particular graph is that if I move R4 way out to infinity, so if I move R4 way out here somewhere, this particular function will never ever go to 0. So just a quick math refresher. So I'm looking at this reciprocal function. If x is equal to 0, okay, it's an undefined function. So that means that the y-axis is an asymptote. All right, can't divide by 0. So that means the graph is never going to touch there. Similarly, if we look at this function, what happens if I make x really, really large? Let's say 1,000,000 or 1,000,000,000. It's still 1 divided by. It's going to be a really small number, but it's never ever going to be 0, which also means the x-axis is an asymptote. So what does that mean in terms of the x and y-axis being asymptotes? So because x and y-axes are asymptotes, two things occur. A, as r approaches 0, so as they approach or get closer and closer to each other, so if you're to dig down to the core of the Earth, the force due to gravity gets really, really large. So we could say it approaches infinity, all right, which essentially would crush you. B, as, let's change that, as r approaches 0, sorry. Going the other direction then, as r gets really big, so let's say it goes to infinity, a very, very large number, 1,000,000 or 1,000,000,000, well, the force due to gravity will approximately be 0. So the force due to gravity is never ever going to be 0 because the x-axis is an asymptote, so it is going to get very, very close. So what does that mean? That means that the farther you get from Earth, the less and less the gravitational influence acts on you. So you have Earth. Okay, if I'm right here, I feel force due to gravity. If I'm right here, I feel it less, and so on and so forth. So Earth will always be acting on you. So that's why it's so difficult to find a place where gravity is equal to 0. We talk about weightlessness, but when you're including the moon is always influencing you, Mars is always influencing you, the sun's always influencing you, all those influences, it's so tough to find that balance. So when we talk about weightlessness, we're really talking about a very, very low level of force due to gravity, because it's constantly changing because the planets are always changing. So there is your behavior. This is a more in-depth analysis. Grade 11, you just did the calculation. Grade 12, you need to be able to discuss and understand exactly what's going on with this particular relationship. So moving on to the next video.